Afternoon, everybody. So, shall start our discussion on the communication aspect that we have represented in this block diagram. We shall start from the first block, that is the source coding. So actually, as we have told here, that source coding is to reduce redundancy, but generally it also means that we have to keep intact the information. On the other hand, basically, in the channel coding, we add redundancy. Now, these two redundancies are a little bit different. Here, the source symbols or the content was unknown. So this redundancy was unknown. So now when we are doing channel coding, when we add redundancy here, so this is basically a known redundancy. So a deliberate pattern is added. So that is the difference between the two coder, source coder and the channel coder. So we will not go into the detail of this coding. However, because this course deals with all the communication aspects. In analog communication, of course, we have analog signals, like say voltage, current, or any other signal. In case of mechanical, there will be like pressure could be a signal. Generally, there are pressure transmitter used in various communication link as well, because that has the added advantage that in inflammable environment we can transmit pressure signals using fluids, non-inflammable fluids, so thereby avoiding any voltage or current, that is the electromagnetic energy. Now, in analog part, of course, we also have these blocks. In case of any analog communication channel, generally there may be a source encoder, and for the channel encoder is usually built into the analog front end and along with the modulator. So that is for analog communication. How the source encoder works in analog communication? Usually, in case of analog communications, we transmit one, say, signal which is representing a voltage. Now, again, we may encode this voltage in terms of various other analog parameter. Maybe we can represent voltage in terms of current, because current has the added advantage that it maintains continuity, and also generally there a less chance of having a floating point.
Hello, sir.
Yes.
So
Yeah.
your voice is not audible.
Okay. Yeah, but I have switched on. Is it little softer?
Yes, sir, there is continuous background noise. Yes, now it's okay.
So we can hear it, but it's difficult to interpret what you are saying.
Background noise. Yeah, now the background noise reduced.
Yeah, yes, sir,
Okay.
much reduced. Okay.
It's still there. All right. I mean, what kind of noise? There is no noise. I cannot. Maybe the PC I'm using a PC. The PC fan is creating some noise, most probably. Or there is a tick-tock kind of noise.
Sir, the internal buzz is there.
Okay, that may be due to the microphone that I am using, but then today I have only this microphone. Let me connect it again. Yes, is it improved? Okay, let me speak little louder. Okay.
Okay, sir.
So in case of analog signal, analog communication, also we have kind of coding, as I am talking, that maybe our signal is like a voltage, okay, but to voltage may not be transmitted from one end to another end reliably. So therefore, people also transfer this voltage to a analog to a proportional current, or maybe a proportional frequency, or maybe a proportional phase. So the phase frequency has the added advantage that generally they are not attenuated, and when in presence of signal attenuations in the path, that can be detected more reliably than the voltage itself. So that is in the analog. So that part is usually built in along with the analog front end itself. There could be even in digital also the raw signal. If we want to transmit the raw digital signal instead of say source coding or the channel coding block, so the raw digital signals for a short distance can also be transmitted, but then it is transmitted usually having some kind of level shift or kind of coded digital signal. So how it is coded? Like say digital bits are usually represented by symbols, that binary symbols 0 and 1. However, if I represent 0 by 0 voltage directly, then there is a chance that 0 is shifted and also may be confused with a signal channel loss. So that means if your wires are cut in between and there is no signal, so that can be confused with the 0 signal. So essentially to avoid that, therefore 0 could be 0 is coded by an active signals. Maybe say plus 5 volt can be taken as 0 and 1 can be taken as minus 5 volt, or maybe minus 5 volt can be taken as 0 or plus 5 volt can be taken as 0. So essentially some kind of coding is done even in the rudimentary kind of signals. Of course, nowadays when we comes to computer communication, so we handle not only signals which are generated by certain kind of devices or process, but that is generated by many other operations. Like I want to transmit one word file, okay, so this has a lot of characters. So usually characters are again coded simply. You may be knowing that there is some code is there. There is American standard and European standards for character coding. So that means each of these A, B, C, D, etc. is coded, and that is usually coded by a 7-bit or 8-bit number. And then the binary string is generated and then that is transmitted. So that is the primary mode of coding of characters. Those are popularly known as ASCII coding, ASCII. So, but here, of course, by source coding, we mean that we have data which is available by a modern data concentrator or a device which has taken a lot of inputs from various operations and then collected the data in a file sort of uh, or in a chunk. So that need to be coded. So that kind of source coding is usually we will be concerned with. So source coding. So the purpose of source coding source coding is to reduce the bit budget or bandwidth requirement, because we know that the more data that we want to transmit, we require more bandwidth. While the necessary information in the symbol remain intact and can uniquely decode it. So, so this way, because of this uniqueness, actually source coding, though the process is very similar to compression, however, it is little bit different because of this unique requirement. So generally in communication, the source coding block refers to the coding schemes which are done in a lossless manner. So because of this uniqueness requirement, it is to some extent different from data compression. In general, it is similar to lossless compression.
Sir,
Yes.
sir, what is bit budget and bandwidth requirement?
Yeah. To represent an information, we require certain number of symbols, and in case of uh, binary representations, the symbols will vary. Like say the bit budget for a set of source symbol essentially is the number of bits or number of binary symbols required to represent. So like say, if I have 2 bits, I can have 4 different symbols. Okay, so 4 messages can be represented by 2 bit. Okay, so uniquely they can be represented. 00 is one message, 01 is one message, 10 is another message, 11 is another message. So if I have 4 distinct messages, they can be represented by a 2-bit symbol, because this 2-bit symbol has 4 states. These are the different states of occurrence of this 2-bit combination. Okay, so each place is holding place can be 1 or 0, so therefore that is 4. So for example, for 3-bit there can be 8 messages. In general, say if we have n, so this is we can see that log 8 to the base 2 equal to 3. So here say log 4 to the base 2 equal to 2. So for binary bit stream message, of n bit, message of n messages, require log n to the base 2 binary digits. Okay, so therefore if we want to have more messages, then we require our bit budget is more. Usually between the message, if there is some kind of redundancy, then what happens, we can reduce the bit budget corresponding to the number of messages. This is true when our messages are unique. So that means by this 2-bit symbol, I can represent 4 unique messages. By this 3-bit symbol, I can represent 8 unique messages. So n unique messages can be represented by log n to the base 2 binary digits.
Excuse me, sir.
Yes.
So what is the meaning of this redundancy we are using?
Which one?
So what's the meaning of redundancy? Like you said that source coding reduces the redundancy in the signal.
Yeah. That will redundancy means actually part of the one message can be computed from another message. Okay. Like say I am currently speaking. So therefore, in my utterance or like here, or maybe I can explain from this, like I want to transmit this, this one. I have a fat cat. Okay. So how many symbols are there? So there is one I. Okay. So I is 1, H is 1, A 1, 2, 3, 4, 4 number of A. Then B there is 1, E1 and C1, F1. We shall discuss more on this. So as you can see that if I want to transmit and of course blank, 1, 2, 3, 4, 4 blanks are there. Okay. So therefore, the most probable in this message, the most probable symbols are A 4 times and the blank 4 times. Okay. And the next probable is T 2 times, occurring 2 times. Rest all of these symbols I, H, V, E, C, F. So all are occurring only once. So therefore, occurrence of A has a redundancy. So it is not unique. So that means the symbol A is occurring again with respect to this. So I can probably represent A by a symbol, by a number, which is having the reduced bit 1. So that we shall discuss the philosophy. So therefore, if I want to make the information content of this signal to be computed, then actually I have to look at the occurrence of these symbols. So there are how many occurrences? We have 4, 2, 6, 7, 8, 9, 10, 14, 15, 16. So 16 occurrences are 16 events. Okay. Now every event does not no more than 16. Is it 16? 4, 2, 6, 7, 8, 9, 10. Yeah, 16 occurrences. Out of that, how many symbols we have? 1, 2, 3, 4, 5, 6, 7, 8, 9 symbols are there. 9 symbols occurring 16 times. Had it been 16 symbols, different symbols occurring 16 times, then we can say every occurrence in this event is an innovation. So there is no dependence of any of these occurrence with another occurrence. But it is not so. Because A has occurred, the event A or the symbol A has occurred 4 times, the blank has occurred 4 times, and T has occurred 2 times. So therefore, these symbols we can say has the most probable occurrences within the 16. Okay, so the information content which could be possible within 16 occurrences is not full because there are redundancy of occurrences. All right, so it is like your that tossing the die example Okay, dice, tossing the dice example. So there are 6 different phases that can occur. Now you are tossing it, so every time there will be 1. But if I toss more than 6 times, even if I toss 6 times, there could be multiple occurrences of one side. But then if I go on tossing more, I will see that there will be more number of occurrences. Now here I have 16 letters. So within this, I can say that there is certain amount of redundancies are there. Okay. Now we can quantify this by computing the probability of occurrence of each of these symbols. So what would be the probability of occurrence of this? This will be 1 by 16. This is 1 by 16. This is 4 by 16. Okay. So like that we can compute the probability of the occurrences as well. Now the information content of any message is dependent on this probability. So usually depends on the probability of occurrence. Of various symbols. The information I in general of any signal or any message or any event information I is usually inverse to the probability. So that the more probable an event, there is less information. So I have here all O or all zeros. So this does not have, there is no change. Okay. So therefore, basically if I say compute the discrete probability, so 6 times 0 has occurred 6 times out of the 6 occurrences. The probability is 1. So the information content in this is 0. Okay. So 0 here is occurring 6 by 6. So that is equal to 1. So there is no new or no innovation is here. So therefore no information is added by the next event. So because the next event is same, okay. Actually, we will not discuss in detail, but little bit of this maybe is we will discuss. So where P is the probability.
So what is meant by more or less information content?
Yeah, less information means basically we can predict the next event from the past event completely. Okay. So therefore there is no information. So for n bit, P can be 1 by n or 1 by P equal to n. So therefore, to encode, to represent each message of in bit, with probability P, needs log 1 by P to the base 2 bits. So this is the ultimate requirement. Usually the coding schemes generally cannot reach this. They reach to this level as close as possible. And that way we call the coding efficiency. So for binary system, this is I equal to log 1 by P to this. This is for binary system. So there is another terminology which is very similar, is called entropy. Now entropy of a set of symbols, of a source symbols, of a set of source symbols. Most of the time we call it a source. Say M1, M2, Mn with say P1, P2, Pn, Hm is given by I equal to 1 to n Pi II bits. So II, where II is given that log of 1 by Pi bits. So that is the information content.
So here, what is the base of the log that we are taking? Is it natural E or any other number? Right?
Yes.
2.
No.
Okay, sir.
Okay. This is we have a set of source symbols M1, M2 up to Mn. Okay, and they have the probability P1, P2, and Pn. So then the information of each of these symbols corresponding to this I equal to 1 to n. So I this is I equal to 1 to n. II is equal to log of 1 by Pi. Okay, so and then the entropy of a set of source symbol is defined as the summation of the information content probabilistically. Okay, so that means if we predict that how many times it will occur a particular event, so that will be given by this probability Pi, and the information content II, that is multiplied. So that means the ith state gives an information Pi into II, and this that will occur, that will need to be summed for all the symbols. So I equal to 1 to n. This is the summation. So because we have represented n in terms of p, so we can as well write hm equal to I equal to 1 to p pi log 1 by pi. So we are replacing II by pi, and then I becomes I equal to 1 to p, the probability. Because p equal to 1 by n, that we have put. So that is equal to minus sigma I equal to, okay, I think 1 by p. Okay, this we may not put it like this. I think 1 by 1 I equal to 1 to n. That is better. I equal to 1 to n and pi log pi. Bits. So these are the two important terminology that we will use. One is information and another is entropy. While the source coding, we shall discuss about source coding. So entropy is maximum when all messages are equiprobable. So this is again can be proven through a Lagrangian expansion. Okay, but I am not doing it. So this is just I am writing entropy is maximum when all messages are equiprobable. With that small background, we shall start our discussion on source coding. So there are two requirements of source coding, that they need to be as efficient as possible, and however they need to be uniquely decodable. So the requirements of source coding. Is to achieve an efficient representation of source symbols in terms of information content. And also is to achieve an efficient and also uniquely also to be uniquely decodable. So for example,
Sir, what is bandwidth?
yes,
Sir, what is bandwidth requirement?
actually bandwidth requirement, bandwidth means if we want to bandwidth requirement is related to the rate of bits to be transmitted. Okay, so that means if our source is producing say 10 to the power 6 bits per second. Okay, then what will happen? Then basically we have to send this 10 to the power 6 bits per second from one place to another place. So therefore, if I transmit this bits through a analog channel, then what will happen? On the other side, the shape of the bits need to be intact. Like say, I have 10 to the power 6 bits. Suppose I am not doing any compression, etc. So I am simply want to transmit the bit stream. So suppose it is like this, and this kind of 10 to the power 6 bits are coming per second. So therefore this becomes 1 microsecond. Okay, so this becomes 1 microsecond interval. Now, so on the other side, this is the say source side I am sending. So on the other side of this channel, suppose I am receiving these bits. Now what will happen? Actually, this represents a representation of certain voltage levels. Suppose I am transmitting voltage. It could be many other things as well, but simplest would be suppose voltage. Okay. So then I have to recover this on the receiving end. So ideally, this pattern should be there. Now what will happen if the bandwidth is basically given in hertz, okay? So bandwidth is represented in hertz. Now if it is for an analog channel, if it is not maintained, then what will happen? So first I have transmitted 1, then I have transmitted 0. However, because this channel cannot transmit at this rate, so therefore, while the 1 has been reached here, okay, so the 0 will be partially overlapped. So 0 will be overlapped. The next one may start here. And if I have very severe cases, it may happen that these two ones are merged, and I may get something of, say, this kind of signal on the receiving end. Okay, so here is supposed to be 1 and this supposed to be 0. Now usually this happens if the analog channel cannot have enough bandwidth. So bandwidth is generally represented physically by, if I want to tell further, then a channel, physical electrical channel would be represented by a transmission line. Okay. And it has a particular time. There would be some resistance also. So depending on this capacitance and L values, actually it will require certain time to reach. Now before that, this charging discharging occurs through that capacitor, I have sent the next signal. So therefore this kind of shape is occurring. So therefore for an analog, so this is for an analog channel. Now this is the physical bandwidth of the cable or the wires that I am explaining. Now the bandwidth requirement may be also given by the other devices, those are connected to this end. So that also may be limited, maybe an amplifier, maybe a other kind of devices, that filter, etc. So those may limit the bandwidth. So overall, so that bandwidth means that I have to basically, digital bandwidth is that the bit rate. Bit rate is the bandwidth. Now the analog bandwidth and this bit rate is usually related. So they are related in certain fashion that we shall discuss later. Okay, when we shall discuss about transmission media. Because again, then we have to divert, to a great extent to a different topic. So however, physically, so bandwidth requirement is there. So that is generally given by the successful transmission of certain bits from one end to another end at a given rate. For example, here the rate was 10 to the power 6 bits per second. So therefore, we can crudely represent the bit rate to the bandwidth. Is it all right? Okay. So because suppose this represent, actually you cannot represent a perfect square. Am I clear? Are you listening? I mean, those who has asked the question. Yes, who has asked the question?
Yes.
Are you listening?
Yes, sir.
You are listening, no? So further, if I want to explain, so this is say xt. Okay. So further, if I explain this, not in giving to physical thing, mathematical, then it is like this. So I have to represent this temporal profile, this time profile of a signal xt. Now bandwidth is a definition that is given in the frequency domain, okay, in terms of hertz. Now if I take the Fourier transform, okay, so then it will look like this. This is a square pulse, okay. So if I take the Fourier transform, we can take the Fourier transform because it frequency domain representation will be given by the, so it is given by that. So therefore, to represent this signal, at least I require this much of bandwidth. Though ideally a perfect square pulse can be represented by an infinite bandwidth. That is the basic of signal systems. Okay. Now that's why I was representing a physical media always basically distort this pulse. You cannot get a perfect square pulse on the other end. So however, if instead of like this, had it been like this, so then we can always recover this 1 and 0 by putting a threshold here. Okay. So that means below this is 0, above this is 1, something like that. So that way, so that means this is basically this media, whatever bandwidth it